this video we're going to take a little bit more of a look into concentration time graphs. So we mentioned in the first video that we can find the rate of reaction by finding the gradient at a particular time on a concentration time graph. What we're going to look at now is how the shape of a concentration time graph might give us some indication of the order of the reaction. And one of the factors we will need to look at when we're thinking about this is going to be something called the half-life. And half-life is the time taken for a concentration to fall by half. So it doesn't have to be from the very start. So consecutive half-lives would be, for example, if I started at 10, then I went, how long would it take to fall to 5? How long would it take from fall from 5 to 2.5, and then from 2.5 to 1.25 moles per decimeter cubed? They would be consecutive half-lives, but they don't have to be consecutive. So I could look at from 10 to 5, and then how long it takes to go from 8 to 4, and then how long it takes to go from 6 to 3, and this would be going down the y-axis in chunks that half and seeing how long it took on the x-axis in time for that to happen. So half-life is going to be an important concept for these concentration time graphs. It's really important that you know what we're plotting here, because there are two types of graphs in this pack, and this is a concentration against time. And when they say concentration against time, then the first thing is going on the y-axis and the second thing on the x-axis. So how does concentration vary with time? So let's take each type of order one at a time. So if we were to look at something that was zero order with respect to A, i.e. what that means to us is that A has no effect on the rate. So the concentration of A doesn't actually affect the speed at which the reaction happens. Remember that the rate on these graphs is the gradient. So at all times, the gradient is the same. Well, that means that this is a straight line. But we have to remember that concentration of reactants does actually fall during a reaction. So it's not a straight horizontal line, it is a straight diagonal line. Concentration is going to fall during the reaction. So let's draw a line representing the concentration of A falling over time. So we should have something like that. The concentration starts off high because it's a reactant and gradually falls over time, but it falls at the same rate at all times. So if you were to measure the gradient by doing dy by dx, what you can see is that the gradient is the same at all times. So we would say that the rate, or the gradient, is the same for all concentrations of A, but the concentration of a reactant is falling over time. So I'm just going to put some notes at the side of this graph. So what we've got there is to say that concentration of reactant A does fall, that's why our line goes down, but that the rate, the gradient, is the same at all concentrations of A, so whether at the top or the bottom, whether we've got lots of A or a little bit of A, it's not seeming to affect the rate. So that's a little bit different to what we said in our A1 notes, where rate always increases when concentration increases. If it's zero order, then this thing isn't actually occurring in the rate determining step. So we say rate is independent of the concentration of A. What would it be different then if a reactant was first order? So let's pause the video and label the axes and then have a think about the graph shape. So what we have is a curve. It's an exponential decay curve if you've studied those in physics. And what we can see if we were to look at this is something very interesting happens when we consider the half-life. So what we say here is that the half-life is constant when a reaction is first order. And what that means is if in an exam you get asked to prove using one of these graphs the order, you'll normally find that the answer is that it's first order because you're going to have half-lives that are constant. So what does that look like? So if I were to plot on some half-lives, what you can see in the first one is I've gone from 100 to 50. I've gone from where it's at 100 to where it's at 50, and I've measured the difference in those time intervals. So it was at time 0 when the concentration was 100, and then it was here when the concentration was 50, and that time interval is the time it took to fall from a concentration of 100 to a concentration of 50. Now, I can then measure a second half-life by measuring the time it takes for that concentration to fall from 50 to 25. So it starts at 50 and it ends at 25. How long does it take to do that time interval? And what we can notice is that those two time intervals are identical. When we're doing this really for real, the graph might be a little bit out, and so don't expect them to be exactly the same number. So maybe 200 and then 195 seconds. As long as they're not going in a trend, they're not all increasing if you keep measuring them, then they are constant. So we've got from 100 to 50 and then from 50 to 25. We could do another one from 25 to 12.5, and that one would still be the same as well. Okay, so if a graph is showing first order with respect to A and you measure the half-lives, you'll find that the half-life is constant. So how would it be different if it was second order? So label the axes again yourself and let's have a look at how that graph would be different. So here you go. What you'll notice is this looks very similar to the first order graph, but it's just that bit steeper because the effect of the concentration is much more pronounced on the rate. So the reaction is much faster at the start because it has a squared effect because it's second order, and much slower at the end. So this is a much steeper graph. Now if we were to measure half-lives on this graph, what you would notice is that the half-lives will get bigger. So if it's a second order and you measure your half-lives, then what you'll find is that the half-lives will increase. And that's how you will know that it's not first order. So if it's first order, they won't be perfectly exactly the same, but you will see that they will be roughly the same. Whereas if it's second order, what you're going to see is that the half-lives are going to increase quite a lot. So they might start off at like 50, then they might be 80, then they might be 120. So if the reaction is second order with respect to A, the half-lives will increase. Okay, so what we're going to do now is we're going to put that into practice. We're going to actually do that with a concentration time graph. So how would we do this? We would start with a known concentration of A and B, and to ensure that only one of those reactants is being measured, what we're going to do is we're going to keep one of them really, really big in comparison to the one we're trying to measure. So we're going to keep the concentration of B much larger than the concentration of A, and what that means is that B's concentration remains effectively constant. It's so large, it's effectively zero order because it doesn't change, so it has no effect on the rate. So then we're going to look at the concentration of A at different times during the reaction and plot a graph. This is known as continuous monitoring. So you start your stopwatch and you measure the concentration of A. You might do that if it was something that was acidic. You might do that with a pH meter because pH gives you a measure of acid concentration. If it was coloured, you might use a colorimeter because colour of a solution gives you a measure of its concentration. Yeah, so there's different ways. If it was producing a gas, you might measure the volume of gas being produced at different times. All of these would be continuous monitoring. So you're measuring something continuously at lots of different time intervals. The reaction of bromine and methanoic acid is catalysed by hydrogen ions. Why do you think you can follow this reaction with a colorimeter, bearing in mind what I've just said? There you go. What we find is that because bromine is orange-brown, but all the products are colourless, the intensity of that colour can be used as a measure of the concentration. So what we're going to do is we're going to plot a graph. Well, you're going to plot a graph. So we've got a large excess of methanoic acid, and then we've got these different concentrations of bromine that we've measured using a colorimeter over time. Now, because they're a little bit tricky to plot, what we're going to do is multiply them all by 1,000 to make them easier to plot. So we're going to end up with 10, 9, 8, 7, 6, 5, 4, 2.8, 2.0 and 1.3. So we're going to be using these values on our axis. We're going to plot the concentration, labelling the axis exactly as it's labelled there up the side, and the time along the bottom. So pause the video, plot that graph, and then see if you can do the things it asks you to do at the bottom of the page. So hopefully you've managed to draw the graph and plot on the required aspects. So we were looking for you to put onto your graph the points, draw a smooth curve, label your axes, and my time axis is on there labelled, it's just right off the end of the page, and you can't quite see it. And then I've drawn on half-lives. I've drawn one on from between 10 and 5 here, 198 seconds, and then I've drawn another one on between 8 and 4, and that one is 204 seconds. I've drawn one on between 5 and 2.5, that's this one here, that's 204 seconds. And I've also drawn on tangents to find the rates at different times. So what we're going to do is we're going to go back to the notes and have a look at all of that information in the notes. So I've got 198 seconds and 204 seconds and 204 seconds as my 3 half-lives. So there you go, from the graph we had those 3 half-lives, and we can see that they are basically constant, although we've got this 198. We've got 2 at 204, and they're definitely not increasing significantly, which is what would be second order. I've measured the rate at time equals 0. You can always rewind and have a look at that graph again. And I measured it at time equals 300 and time equals 550. I drew tangents to the curve at these times. You can see that the rate is slowing down, which makes sense because the graph was levelling off. So that's this end of this video looking at concentration time graphs.